Hey guys. Well, let me tell you, this is the, I think, third time that I have tried to record this lesson. So third time's the charm, right? We're going to be talking about exponential functions in this lesson. We're going to be talking about the graphs of exponential growth and exponential decay graphs, but also the attributes of those graphs. And some things are old topics that come back, which is great. So first of all, a general form for exponential growth or decay would be an equation in the form y equals a times b to the x. Now this is a really general form, but the important piece of that equation is that your variable x is up in the exponent position above a base, and then the only thing that we accept is that the base is a positive number and it can't be a 1. So anything above 0, just not 1, because a base of 1 wouldn't grow or decay because it would just stay flat. So that's pretty boring. All right, so the next vocab piece is how do we determine whether we have exponential growth or exponential decay? Well, the graph makes it pretty obvious in most cases. Exponential growth would grow without bound as you move towards positive infinity. We'll talk about in behavior later. But the way the function works out is that your base is greater than 1. So I will put a few examples here. So maybe you have like 3 to the x power, or 5 to the x power, or some kids get tricked here, 3 halves to the x power. That would also be an example of an exponential growth because 3 halves is really 1.5, which is greater than 1. So what about exponential decay? Well, again, the picture is kind of telling. In most cases, you could see it decaying off as you approach infinity for the right behavior. But the idea for the function, for the equation, is that your base is between 0 and 1. Now remember, it can't be 0 and it can't be 1, but it's between 0 and 1. So some examples of that would be like we see here, 1/2 to the x power, or possibilities are endless, right? 2/3 to the x power, or sometimes they're written as decimals, so like 0.4 to the x power. Those would all be examples of exponential decay, which you could clearly tell without graphing it just by the equation. So this next question, every time we investigate a function, we typically try to pull our technology in to help us out, and that's what we're going to do here. So we're going to go to our calculator, and we're going to type in 2 to the x power into y1. So using that caret key, this is the caret key, it brings you up to the exponent, and then use your your variable key of x. And then let's just peek at the graph. So I'm in the standard viewing window, that -10 to 10 window, and I can clearly see that this is exponential growth. We'll talk more about that in a minute. Now, as far as getting good points, well, I could pretty easily plug in some numbers to that function, but when I have my technology sitting here waiting for me, why not just use it? So I'm going to pull a few of those points and then plot them, obviously. And then everybody knows I'm going to do a really terrible job of graphing, but that's okay. So I'm just going to go with a few points. Let's see, I think I remember there being like a -2, 0, -1, a 0, a 1, and you can go as far into the list as you wanted to. But let's see, -2 power would be a 0.25. You could just read this off the calculator. -1 power is a 0.5, this is a 1, and this is a 2. I'm doing those quickly mentally because I'm just plugging in the proper exponent. And then, like this, any of this matters because y'all know what's going to happen. I'm going to graph it. It's going to be awful. The good news is I do have a calculator to kind of assist me with what it should look like. So that way, even if my graph is horrible, I have a little bit of... I don't want to talk because I'm actually doing really good. Wow! That might be the finest exponential growth, oops, spoiler alert, growth question that I've ever graphed. Okay, this is most definitely an exponential growth. From the picture, we were kind of thinking that, but let's talk about the base. The base, the thing that's holding the exponent up, is a 2. So that's how we know it's an exponential growth. The Y-intercept is something that you can pull straight out of the calculator. The Y-intercept is where the x value is a 0. So there's a Y-intercept at 0, 1. Old concept, but it's coming back because we have a new function. Remember, domain is from left to right. How far does this function stretch? And this function goes forever to the left and forever to the right. So that's great news. Easy domain, -infinity to infinity. Now, the range is a little weird. This is going to be new for us. The concept of range is not new. We know that range measures low to high. That's an A. So hard to write sideways on a tablet. All right, so range measures low to high. The range, it kind of appears like it starts at 0, but when we start thinking about the function, and if we look at the table, it doesn't actually get to 0. It just gets really, really, really small and close to 0. So the range starts at 0, kind of, and because it doesn't hit 0, we use a parenthesis. So that's how you indicate that it's approaching a height of 0 on that bottom of the range, but it doesn't actually get there. It definitely goes up forever, though. That one's obvious. Now that line that I kind of marked with this red dash, that's called the horizontal asymptote. It kind of behaves like an invisible fence, and really it's an end behavior question. But this line would have the equation y equals 0. So kind of like an invisible fence. That's a weird definition for math because it's not like it can't cross an asymptote. These particular functions don't cross their asymptotes. All right, and I know that's a funny looking word, so good luck spelling that. End behavior, old concept, same stamp that we used to see in end behavior, so we're going to write that out. F of x approaches blank, and then I always do left behavior first, so as x goes to negative infinity, and then the other end of end behavior would be the right side. So f of x approaches blank as x goes to positive infinity, the right. So just to jog your memory here, this means left side, and this means right side. So they're asking us what height is your function approaching on the left side and on the right side. So on the left side here, it's approaching a height of 0. It's approaching the asymptote level. On the right side of your function, it's just up, 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 up forever. So it's approaching a height of infinity. So that's interesting. I saw that asymptote at y equals 0 kind of show up a few places in my other characteristics, and we'll discuss this later, how that asymptote line is actually really important to the problem. So here, same idea. I'm trying to save a little bit of time on my lesson because I know these get long. You could type this into y1, and then you could go to your table and you can get a bunch of points, right? That would be totally fine. Let's pretend I did that. So I should be able to evaluate this in my head. I'm going to use those same x values that I used on the last question. Negative 2 power, let's see, that would flip it and square it, so that'd be a 9. The negative first power would flip it and take it to the first power, so it'd be a 3. 0 power is always a 1, and then 1/3 of the 1 is 0.33. So when I plot these ordered pairs, we're going to see me struggle through graphing like normal. I have a lot of confidence after that first one I graphed, but I have a feeling I should not be so confident anymore because decay are harder. Spoiler alert again, this is a decay. Decay are harder for me to graph. See, I picked up my pen and now it's... Wow! See, the third time I've done this lesson in the last couple days really paid off, man. Okay, so this is clearly a decay from the picture. But the reason I can tell from the equation that it's a decay is because your base is a 1/3. And by definition, if your base is between a 0 and a 1, you have an exponential decay. The y-intercept is one of the ordered pairs that I chose to plot, where x equals 0. So that would be at 0, 1 again. Domain, once again, goes forever. It goes forever to the left and forever to the right. So I know usually this is the point in the class where a kid would ask, hey, is domain always going to be that? For these functions, yes. Domain will always be negative infinity to positive infinity for an exponential growth and decay function. All right, let's talk about that range. Once again, we seem to have this weird invisible fence line going on down here at what we now know is called the horizontal asymptote. So once again, your range is low to high, right? That's still the same definition for range, low to high y values. So once again, the range tries to get to 0 but doesn't get there, so we use a parenthesis. 0 to infinity. So the last two functions have had the exact same domain, which will always happen, and they've actually had the same range. We'll talk in a minute about whether it's always going to be that. We kind of already talked about this too. The horizontal asymptote is again at that line y equals 0. And then end behavior, everybody's favorite. I'm going to write out my template for left and right end behavior. So I always do left side first. I know, it's very annoying to write this out, but the actual end behavior is like a paragraph of math. So this is the shortcut. All right, so this says left and this says right. So let's look there. So on the left side, my function is approaching a height of up, 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 up. So it goes to infinity. And then on the right side, my function is approaching a height of the asymptote, which is approaching a height of 0. So just like in the last question, one of the end behaviors went off to infinity, and one of the end behaviors went towards the asymptote. It's not always left does this, right does this. It depends on whether it's growth or decay. So again, we'll make some more connections later on in the lesson. This one always tricks kids, okay? This one I will go back to my technology for. 3/4 to the negative x power. So right away, I hope you notice something kind of weird. Parentheses, Abruzzo. All right, 3/4. A lot of kids look at that and go, oh, decay, because it's got a base that's between 0 and 1. And then when they graph it, they see what is clearly a growth. And they're like, well, wait a minute. Why is it a growth? Well, for now, let's grab some points. I'm going to grab those same ordered pairs, -2, -1, 0, and 1. Like, I'm going to remember this. All right, 0.56, 0.75. Oh, boy. Maybe I'll remember. Oh, no, I'm not going to pull those ordered pairs because they told me to choose -1, which was 0.75. 0 would be a 1, of course. 1 would be a 1.3 repeating. And that last one, I always forget. It's 1.7 something. Yeah, 1.78. All right, so we're graphing. Full screen time. All right. I never know if my face disappears while that happens. On my screen, my camera went off. It's probably better for everybody. Okay, -1.75. 0, 1. 1, 1.3. And 2, 1.78. Now, I haven't even plotted points very well, but what can I tell from my calculator was it actually was a growth. It's slow to grow. All right, let's talk about why it's a growth, first of all. So, when we have a negative exponent like this, remember negative exponents take fractions and they flip them around to the reciprocal, right? So the 4 would come up top, 3 would go down the bottom. So this function is really a 4/3 to the x power. So the base is actually a 4/3, which is greater than 1. So that was a bit of a tricky question. And you can't even read what I wrote. Let's try that again. So I've seen something like that on the SAT, so watch out. They do try to sneak those in. Once again, the y-intercept has been at 0, 1. We'll discuss in a moment whether that's always going to be true. Domain, always negative infinity to infinity. It's a nice question. And then once again, we have this range that, approaches the height of 0 for the starting and then goes off to infinity. So the last 3 questions, while they have had very different functions, they have had those things in common. Once again, the horizontal asymptote was at the line y = 0. And then we have our end behavior. This is where I really miss being in class because these are really great questions for discussion. So hopefully we get a chance to do, oops, what did I do that for? I know what behavior I want here. I want left first. And then I want right next. All right, so on the left side, our function is approaching a height of the asymptote, which is 0 again. And then on the right side, it'll be up here, it's approaching a height of off to infinity, so we're going to put infinity. Fancy for up. Okay, so let me talk to myself for a minute. All right, is it always going to be that? So we've had 3 questions in a row where our intercept was at 1, our asymptote was at y = 0, one of our end behaviors went to the 0 and 1 to infinity, the range was 0 to infinity. Well, we haven't discussed yet what happens when you transform these. So what if you move it to the right or to the left, or what if you move it up or down? We're going to see some changes, right? So if we were to move this function to the right or left, that's not really going to change much other than the y-intercept. Where it crosses the y-axis will be different, but that's about it. If we move the function up, that's going to change a whole lot of things. It'll change the y-intercept, of course, but it's going to change where the horizontal asymptote is located, which means the range will be different, which means one of the end behaviors will be different. The good news is they're all going to match. So let's talk about that here. Let's try to connect some ideas. Remember that in our other functions, when we saw x minus h, in this case it'll be up in the parentheses, that meant a horizontal shift, right? Horizontal shift. So H is horizontal. There's a built-in negative. And then this plus K off to the side would be a vertical shift. So when I look at this example over here, and I see 2 to the x minus 1 power, this guy was shifted right 1. Remember, there's a built-in negative there. And then on the end, we have a negative 4, which I know vertically shifts it down 4. Okay, so that's nice. Without even touching the calculator, I could take an old concept and apply it to this new function. But, you know, let's be safe and let's touch the calculator finally. 2 to the x minus 1 minus 4. 2, and then use your caret. If you're on an older calculator, use parentheses around your exponent. If you're on a newer one, you don't need to, but do make sure you use a subtraction sign there, as well as right here with the minus 4. So we thought this was shifted to the right 1 and down 4. I can definitely see the down 4 shift, and it's even more apparent if you go to your table. So if you look at your table and you start kind of scrolling back in the table, you'll see these y's that are like approaching negative 4, and I know this one appears to be negative 4, but what if you highlight over it, it's really negative 3.999. You know, so your calculator ends up truncating and rounding because it runs out of pixel space. But I do see that down 4 shift. Okay, cool. So what that tells me is the asymptote, instead of being at 0, now it's going to be down here at negative 4. I'm going to actually fill that in right now. So y equals negative 4 is the new asymptote. I didn't pull any of those points. Well, that's not very helpful. Let's try 0, negative 3.5, 1, negative 3. All right, 0, negative 3.5, 1, negative 3. Okay, I'm just going to fudge it from there. We knew it was an exponential growth because the base was greater than 1. It was a 2. We already know the domain is negative infinity to infinity. No surprise there. But let's talk about the range. Remember, the range is lowest y value to highest y value. Oops. Okay. There we go. So because the asymptote shifted down 4, that means your range starts at, well, and I'm going to say it starts at negative 4, but we know it doesn't actually hit the asymptote. It just approaches it. So range is now a negative 4 to infinity. So I'm going to bust out a highlighter because I think this part's really important. There's some connections that I want you to make. Whatever the k value was, obviously that's the vertical shift, but it's going to affect the range, and it's also going to affect the asymptote. Now, the thing we didn't talk about was end behavior. It would also affect one of the end behavior pieces because remember on the left side there, it's going to approach the asymptote at negative 4. So what's kind of comforting about these problems is once you identify like, oh, down 4, you should see that negative 4 show up a whole bunch of places in the rest of your problem. So that's neat. Which means we shouldn't have to use a calculator. This question, these types of questions show up a lot on the no calculator portion of the SAT because they don't care that you can type something into a calculator. They care that you understand how the function works. So here we have a function with a base of 9, so a growth, most definitely has not been shifted in any way. There's no h value here and there's no k value of anything. So it's shifted up nothing, right or left nothing. So that's why they wrote none for transformations. But let's take a look at this one who has been shifted. Has been shifted, remember, built-in negative there, so left 4. And then also shifted down 7. I feel like no one can read anything I write today. I'm going to try that one more time. Left 4. Okay. So let's talk about the easy one, domain. Easy, easy. Always negative infinity to infinity, even if you've been shifted or transformed. The range has everything to do with the k value. So there's no reflection. That is kind of the obscure case. If it's been reflected, your range is a little different, but it still would have something to do with the k value. So the fact that we have, a plus 0 here, but we have a negative 7 there, and we have a down 7 shift, affects where the range starts. So this guy, not having shifted up or down any, his range would be from, using a parenthesis again, 0 to infinity, like the first 3 questions we saw, But this one, since it was shifted down 7, the range would actually start at approaching -7 and then goes up to infinity. Because your horizontal asymptote shifted. So this one still has a horizontal asymptote at 0. There's been no shift. But this one, the horizontal asymptote, is at y equals -7. Very important that when we ask you for asymptotes, they are equations of lines. So for these questions, we've been giving you y equals, because they're horizontal asymptotes. We're going to see in an upcoming lesson for logarithms where we have a vertical asymptote. So those would be x equals. All right, I think that was the lesson. You know what? That might have been my best version yet. Third time was the charm, y'all. All right, good luck, everybody.